applied, but I'm not going to go on. Pardon. Oh, okay. I'm sorry. Okay. So uh, it is something which we worked on. It's not limited to that, and I'm not going to talk about the entire thing. Take 2-3 examples, which I feel which is best, which you people can enjoy. Like I said, I expect people to stop me in the middle and ask questions because the workshop is not just another lecture. I hope you'll not disappoint me. Right? Yes? Yes, very good. It said something and stopped. Yeah. Okay. Let us start with some things which what we can do with it. Wonderful things. You look at the UV absorption spectrum. Many of you must have seen UV absorption spectrophotometry. You would have been carrying it out in the lab. Trying to do this with a simple laptop or your Gaussian or something for some, let us say, organic molecule and simulate it, you are getting almost similar. The one which I gave here is something little different, slightly on, for something which is a little bit almost to the same thing, but there are ones which give you almost exactly same also. Okay. So now, this is one of my students, our friend here, may I remember them, Balaya. You know him, I think, right? So anyway, he is simulating the UV spectrum of that. How much time do you take for the UV spectrum for carrying out the simulation? Hardly 10-20 minutes. How much time do you take in the experiment? Like I said again, it doesn't replace the experiment. It is only trying to tell you or help you with the experiment. Remember that part. You have a molecule in your mind, whether you are synthesized it or you are going to synthesize it or you are planned, and you want to know what its absorption is, or you want to know its oscillator strength and all that stuff. Here is a beautiful example of that. IR spectrum, right? Some of these places you don't get the IR spectrophotometer also that easily. Here is one example where the experiment in theory shows, you see, the apparatus, and theoretically you can get almost similar. Okay. So we are able to simulate almost similar kind of spectrum as the experiment is giving us. NMR, very expensive. In fact, even if you want to get it, you have to send the sample somewhere. IR and UV, at least we can afford it, but NMR is even worse. Okay, here is a with experiment and theoretical. You are able to get almost similar kind of thing. So just see a molecule. We're talking about analytical part, UV, IR, or even NMR. We're able to get it done using the simulation packages. Yeah. Electrochemistry. If you want to get the redox potential, see this cyclic voltammetry. I can get these points by oxidation reduction peaks doing my simulation. Okay. So much straightaway applications, which not only tells you before you do that, but when you finish the experiment and get the spectra also, you can explain why the spectra is behaving the way it is behaving. Because that you will not be able to do it from the experiment. You will get the spectra, may be able to analyze it a bit. But if you are able to do the theoretical time, this one, you will be able to explain it much better. X-ray crystallography, geometry of a molecule. Okay. See this, a complicated geometry of a particular molecule, which this has been synthesized by one of our students, and see the folder. It's a foldamer actually, peptide foldamer, and the blue is the one which comes from theory, and red is from which comes from the X-ray crystallography. See the exact matching. Okay. So we have got all these, like I said, complicated experiments simplified in your theory. And believe me, this doesn't take much time, half an hour, 45 minutes or less than that, depending on the speed of your laptop or computer. Okay, here is a case where we are comparing heat of formation. Heat of formation is a very difficult experiment to finding out the heat of formation. And here is some hundreds of compounds which have been simulated using a particular methodology in theory. There are so many methodologies in theory. We may or may not go into all that depth, but just to tell you that there's something called PM3, and this is the calculated heat of formation versus experimental. Almost a straight line regression analysis. You're getting a straight line. So we are on dot on that particular thing. Dipole. In fact, dipole experiments are quite difficult. You know that. Here is a case where the experiment of pyridine is 2.22, calculated is 1.9. For now, I have started showing you the numbers here. Water 1.85, 1.74. Diethyl ether 1.15, 1.33, and formic acid 1.41, 1.51 simulated. The dipole experiment takes you lots and lots of time. Theoretically, few minutes. And that too with this particular methodology. And only 10% variation. Okay? Right? Right. Next. Yeah. So not only we have been able to decrease the load on instrument and also carry out screening, but we can also carry out studies which cannot be carried out by experimental techniques or difficult to perform. Okay. So some of the experiments, it will be very difficult to perform that. That is like understanding or analyzing. So this is first a screening method. The other is even understanding this one. For example, we are talking about adsorption. I think we have an expert here. So analysis of a dye on a TiO2 surface. How this sits on the surface, how the molecular orbitals, these are the molecular orbitals, right, of the molecule after it has been bombarded with a photon, how the electron transfers that, how the molecular orbital density or the electron density shifts into the TiO2 crystal or the TiO2 semiconductor surface. This is something which you can do experimentally and understand. I mean, theoretically and understand. Experimentally, it is very difficult for you to get into such a depth of that. You can do that, but the depth of understanding exactly how it is behaving, how it is injecting and all that comes from this. Solvation. Something else which you can start doing where the molecules are surrounded by water or solvent molecules and understand how it behaves. Okay. And reaction analysis. This is something which is very important in your physical chemistry, how the activation energy of something like here we have a catalyst but ketoester plus amine going up to the, having a transition energies and going to the product, which is a stable product when compared to this. So how the reaction progresses. This is just not, I mean, I'm not going into details of the particular molecules, but I'm only showing you how these steps can be generated of the reaction as right from catalyst, ketoester, and amine to the final product. Okay. Okay. So let us look at just to tell you that something called internal energy. You are all people who learn thermodynamics, right? You have been learning thermodynamics. So what is this? You have A plus B giving C plus D. Let us say products. The energy of this total energy which is dissipated or absorbed by the vessel, thermodynamics experiment, right, is the total energy of the products subtracted with the reactants. And you say, if it comes out, you say it is exothermic. If it takes in, it is endothermic, right? That's what we. So you are clear about thermodynamics and the reactions. And you are clear about that E1 and E2 has no sense. It is only the total energy which is released or absorbed has making sense, right? There's no energy of that particular molecule. So it's the same principle here. You're docking. What's your docking? Docking is A plus B. Let us say a protease or a protein molecule and a molecule which you think of a drug or an inhibitor is another molecule B. So A is the molecule, let us say, of this enzyme, and B is that particular molecule. They sit together and form the complex. It is since it's not a chemical bond, it's only a hydrogen bonding. It's a weak complex. You get E3. The delta E is E3 minus E1 plus E2, gives you the binding energy of the molecule inside the enzyme. Okay. Yes. Understood, or should I explain again? Is it clear? I'm just telling you the fundamentals of computational chemistry. Please remember that. You understand this, you understand computational chemistry. The last couple of decades which I have been teaching and going around, I have found people making mistakes in these fundamentals. Based on that, I have come with slides of this kind. People come out with some terrific ideas. I don't want to go on explaining what are those here, but I'm just telling you that this is the basics of your molecular drug discovery. This here I'm showing you is the drug discovery. What do? You have this molecule which we call B. I change B, different B molecules, whatever it is. We're talking about some particular drug. We're talking about some particular enzyme. How do you do a drug discovery in particular thing? You want to stop the protein from working, which is, let us say, for a disease. This particular one, let me be more specific. This particular one is the aspartic protease of HIV, this one, a virus. Now, the molecule sits inside that this protease molecule. It makes that protease stop working and doing its duty. And then it doesn't replicate. That aspartic protease is the one which helps for replicating of that virus. I'm just a specific example here. I'll be talking about that in detail a little later. But this molecule goes inside and binds to the enzyme, and then the enzyme doesn't do its duty anymore. It stops. Now, based on this, what do you say? What your delta E should be? If your binding is stronger, right? Then that molecule is better. I'm putting B molecules, say so many molecules here. And how do I discover the drug? I put 20 molecules, and the one which binds strongest to the enzyme is the one which I call the drug. Okay, simple. That is your drug discovery. That's all. So here, two H2O molecules, they are linked to each other. And even this is an enzyme and a organic molecule. But even for two water molecules, if I find out the binding and take the energy of that, you will know the binding of the two water molecules. Simple, very simple thing. So what I'm trying to say is, in general, this computational chemistry, which you know anyway, that is why you are in this workshop, that it is becoming more and more indispensable for this because of such kind of activities. Of course, from the economics point of view also, I should tell you that what was very expensive in 1980s, that's what I first said. When I was in IISc at that time, the computer cost few crores and experiment was cheap. At JRF used to get 600 rupees as his monthly, this one. Today, I think it's 40,000 or something, 45,000. And what is your computer? For 45,000, you get a laptop. So what happened? What changed? The cost of the computers have come down. Cost of the experiment and the salaries have gone up. Your chemicals are very expensive. So what happens? Naturally, we have to start looking for, right? Trying to go for cheaper methodologies, which is doing computers. Okay, that is the reason why computers have taken off. You are now in the era where the intelligence is run by these chips, right? Those days, and also even the computer inputs was completely different. Today it is very easy to give you an input. What you are going to see in Gaussian is very simple when compared to what we were doing earlier. Okay, like I said again, we are going to start with thermodynamics to make you understand. I am talking about some basics because I know many of the people make mistakes in this. So that is the reason why I am going into thermodynamics first. First law of thermodynamics, all of you know, right? Yes? This is morning session, right? You should be having a lot of energy. And I'm an old man and you all are so young people here and my voice is louder. Okay. First law of thermodynamics, yes? Everyone knows that, right? Right, good. So the internal energy of an isolated system is constant. Please remember, this is very important basic part which people make mistakes in computational chemistry. What is this internal energy? If you have an isolated system, what is that internal energy? That internal energy is nothing but the kinetic energy of the system inside that petty or dabba or whatever you call it, the box, plus its potential energy, right? Yes. And if you have it in general, it always kinetic energy is half mv square. So we have no problem with it. It's the potential energy which changes its phase, right? So you will have a general PE, which is called potential energy in general, or if it is gravity, it is mgh or whatever it is. Or okay, is it okay? Right now, let us look at, for example, of this. I have two rubber balls in a box. Okay, two rubber balls in a box. So the total internal energy of the system is kinetic energy plus potential energy. The two for the rubber ball in classical sense, that is Ke1 plus Ke2 plus Pe12, the interaction between these two, that is the gravitational energy. Right? That's okay. As long as it can change my slide, that's okay. Someone is telling something or asking questions? Okay. Can I proceed? Yeah. No, I'm pressing. It's not. Right. So now, if it is charged, then you have the potential energy, which will be Coulombic. Q1, Q2 by R. Right? Okay. So what do you have? We have the kinetic energy of the first ball, kinetic energy of the second ball, plus, I'm talking about something which you learned in 7th class or 8th class. So you should be very comfortable with this, right? I'm not talking any, what you call rocket science or deep quantum mechanics or AI or something of that kind. I'm just talking about simple things, right? I'm a very simple man. I dwell on simple things. It's okay? You know this. So the two balls are interacting inside a box, the kinetic energy of one plus kinetic energy of the other, and the interaction of that. That is its total energy. Can we measure this energy? I just discussed about this little earlier on that. Internal energy cannot be measured. Only the difference can be measured. Right? I carry out a reaction and it generates heat or takes in heat, then I know what it is. But the Ke1 plus Ke2 plus Pe12 has no sense. So it's only the difference. See here. So if you follow a chemical reaction of process through calorimetry, U2 minus U1, which I say energy of the product, right? And so we can talk only about the internal energy difference. We cannot measure the exact internal energy of the system using experimental techniques. We do not know anything about that. Okay, right, good. So let us say for a molecule's differential scanning calorimetry, if you are looking at unfolding of a peptide, some 20 degrees to 90 degrees. So then you measure the at temperature which it happens, and you are able to get the delta H. And it will forward delta E, delta H, delta G, all are okay. You add the temperatures and all that stuff, and this entropy, you get it. But when I talk about thermodynamics, I'm talking about energy of that system. Clear, right? What about a single molecule? Let us come to our actual thing, what we are trying to do. What's a single molecule? What is its energy? Right? What does it have? This is a water molecule. That I think you can recognize, right? Good. What does it have? It is vibrating. It has vibration energy, right? We do not know how much it is, what it is. It is having vibration energy. Next, it has rotation energy, it's rotating. It's moving around. That is what you call the translational energy. And then the electronic energy, this is the toughest thing. Okay, we have a molecule which is rotating, which is moving, which is vibrating, we have that energies, but it is the electronic energy. What is that electronic energy? It is the energy of the electrons inside the total water molecule. How many electrons will be there in that? Array, how many electrons? Bright. Yeah, some. Right, 10. Yeah. All are agreeing with me with 10? 10 is okay? 8 for oxygen and? Very good. So we are on the same platform there. Okay, so we have 10 electrons and 3 nuclei, right? The oxygens and the 2 hydrogens. So kinetic energy of the electrons. Okay. Kinetic energy of the electrons. Potential energy of the electrons attached to the nucleus. So they have, what is the energy there? Is the attraction, right? Potential energy between the electrons, which is the repulsion energy, and repulsion between nucleus. That's all. These are the energies, total energy of that molecule. That is the total energy of this single H2O molecule. Simple. Agreed? It has a vibration, it has rotation, it has translation, and it is electronic. And what is that electronic? That is this. And that is what all your software does. It calculates that. Anyway, we're coming to that. So we use computational chemistry to actually calculate the internal energy of a molecule. That's all. You're not doing bada things. You're estimating that electronic energy of the molecule. And the thing which you should remember, it will give you some energy, which is absolute energy of the total system of the molecule, which has no meaning, but that is the one which you use for your references. So when you run your Gaussian, what does it do? Whether you run your Gaussian or whether you run your whatever softwares, there's hundreds of softwares, depending on the one which you're looking at. Energy is a basic parameter which is going to be given out as an output. What is given? Energy of the system. And that total energy has no meaning unless you use it for trying to do some calculation with it. That absolute energy value will have no meaning. That's what I'm trying to say. I'm not saying that energy has no meaning there. Am I clear? So I have A plus B giving C. So I find out the total energy of A, I find out the total energy of B, I find out the total energy of C. So whatever total energy I have of A has no meaning, B has no meaning, C has no meaning. But C's total energy minus A plus B total energy gives me the actual energy of formation. That has meaning. So something which you have to remember, right? So when you run it, you'll get some minus 6,000, some 270, minus 300, something of that kind, atomic units and all that. That will be This is the fundamental thing which you should remember. Many students have made hundreds of mistakes with this particular part. That is the reason why I have been dwelling on this for some time here. Okay, now let us slightly expand it. How does it, the internal energy is kinetic energy plus potential energy. And what is it calculating at what? What we do is at 0K. Again, which is not our normal life. But I'm just telling you, your theory is at 0K, right? So the kinetic energy of electrons moving around the nuclei, potential energy of electrons attracted to nuclei, nuclear repulsion, and these two together is called electronic energy at 0K. Okay? How to estimate this electronic energy? Now let us come to the actual thing. So we are telling that it is at a very low temperature, it is giving a total energy which has no meaning, but it is there. Right? We have the energy of that. Let us appeal to classical mechanics, something which you people learn in school. Right? What is that? You have a sun and earth moving around the sun. What does it give you? The kinetic energy of earth plus potential energy of sun earth system gives you the total energy of the sun earth system. Right? Any dispute? No. It's okay, right? Now, the solar system is not consisting of only earth alone. We have 8 or 9. If you're an old timer, you will say 9. If you're a new timer, you will say 8. We'll remove the 1, and probably much later generations will remove another 2. Anyway, but right now we have 8 or 9. I still stand with my 9 and tell you that it is there. Okay. Oh, but I think one of my students who prepared it removed that. Okay. So anyway, you have, what is this many body system? You had a one body system. Remember, this is a jargon which you use in quantum mechanics a lot. One body, many body system and all that stuff. What are those? So many body system is the kinetic energy of Mercury, which is moving around, plus the potential energy of Sun-Mercury system, right? Then Venus is kinetic energy of Venus plus potential energy of Sun and Venus. Okay? Everything fine. So each one is separate. You have E1, E2, E3. We do not take into the consideration the interaction between the planets. This is our problem. Had there been no interaction between these planets, very easy life. E1 plus E2 plus E3 plus E4 up to E8 gives me the total energy of the solar system, but it is not that easy. God makes our life a little bit more complicated. It says no. He says no, there's an interaction between that. What is that interaction? The movement of Earth is correlated to Mercury, Venus, etc. Hence, it is not simple potential energy of Earth, Uranus, or Earth, Earth, Sun. It is potential energy of Earth, Mars plus potential of Earth, Venus. There is a correlation between this. That means it just cannot be moving around. The Mars will be correlated to movement of Mercury. The Mercury is correlated to Uranus. All that. Maybe the one Mercury with Uranus is little, but it is still there. So there is a correlation. So the energy is no longer E1 plus E2 plus E3. And what I said, E1 plus E2 plus E3, those chemistry students will know it is the Hartree energy. And Hartree Fock is much later. That is what we are looking at. Anyway, we'll come to that. So one method to solve this is what? Trying to do the n-body problem is very difficult. That means take all the planets and do it at the same time. So what we do, we say convert this n-body problem to each planet moving under the average influence of all other planets, and we call it a field. Instead of taking into consideration A interacting with B, B interacting with C, A interacting with C, multiple things, we say there's a field. Okay? And what is that? That is the average field of a particular planet moving around the sun. So now the n-body problem converts into n one-body problems. So you have Mars moving in that, Mercury moving in that field, Earth moving in that, you have n such problems. And that will give you the total and then the kinetic energy remains. It is there. So that way you get the total energy of the system. I hope you understood this. Okay, there's nothing special. Yeah, nice. We consider that to be a constant. No, it's not constant, but then we have to have approximation of that. That is why you say self-consistent field, which we have to do it again and again and say it reached a self-consistent field, and it says that is the field which we can work with. It's not constant. If it is constant, then it becomes easy for us again. But then it is we make it a pseudo approximate kind of thing, saying that it is constant in that. Yeah. Right. No, but they're interacting with each other, no? Earth doesn't move just with the influence of sun alone. Earth moves around with the influence of Mars, Mercury. Yeah, everything. So that has this very complicated, right? If I have only sun and earth, it's very easy. But I have 8 or 9 planets, then I have to look at interaction of Earth with Mercury, with Mars. So movement is not, it's like your crowd. When you move around, when you are free, I can walk just like that. When I have a crowd, then my thing is going to be different, right? So, yeah, that's what we are doing. But it will not be a simple expression anymore. It will be more complicated. So what I'm trying to say is that the classical mechanics is a problem of this kind, that n-body problem is a problem even in classical mechanics. But unfortunately, in quantum mechanics, they don't highlight that, but that is what we are doing. This is the same thing which we are going to say, which is there in your atomic structure or molecular structure. We'll come to that. Okay? Clear? Good. So that's what we are doing with our water molecule. Imagine that now. We had this example in that box. What are we having? We're having those 3 suns and the electrons. And we say field of 1 electron. 1 electron is moving around the influence of all this nuclei. And that is the total energy, kinetic energy of the electrons plus potential of the nuclear repulsion, all that, each one. And that is what your molecular orbital energy is, or the total energy, adding up the total energies of all the electrons. Okay, it's simple. So you just have to correlate. Okay, I'm sure many of you did have. I asked some question in the morning to some people. You did have quantum mechanics in BSc, right? Your undergraduate. Quantum chemistry, hydrogen atom. Particle in a 3-dimensional box. Yes? Yes or no? Right. How many of you hated it? Oh, yeah, everyone. We're good. So I'm having a lot of enemies now. Yeah. The problem is we do not correlate with simple things. That's the problem. It's a beautiful subject if you really get into it. Okay. I know most of the people who've sat, we were told 10 marks, you forget that part. Right? Array, you don't need to get 100, 90 is sufficient. The rest of organic synthesis, everything is perfect. You can write that. But when it comes to quantum mechanics, hydrogen atom, Bohr's model, this fellow's model, that fellow's model, and then you're not going to understand what the orbit is, right? And then if things make worse, then you will say particle in a box, 1-dimensional, 2-dimensional, 3-dimensional, whatever dimension, why it is doing so, we don't care. Harmonic oscillator, even worse. Legendre polynomials, Laguerre polynomials, Hermite polynomials, makes life miserable. And you hate the lecturer who talked to you about that, obviously, right? And then you say, why did you ever take chemistry? And physics people are even worse. They have a lot of problems. That quantum mechanics is even worse. They go into much more abstract n vector spaces, Hilbert space, and all that stuff. Okay, but it doesn't have to be that way, because that is our basis for your computational chemistry. So what I'm trying to show you is there is a correlation with our regular life with what we are calculating. That is what I'm trying to bring it here. I hope I'm clear up to this point. Okay. We are only, I'm not telling you the calculation, I'm talking about the nature of the calculation right now. Okay, good. So this is the same thing. What you have done in planets, when you can imagine, why don't you imagine that in the molecule? You can imagine a sun, Earth moving around the sun, or even Mercury moving around the sun, but you cannot imagine this in that form. That is not what we are. If you can correlate, then the imagination is also good, right? Okay. Only thing is, like, that's the reason why I know this is one of the most hated equations. But what happens is, if you want to calculate the kinetic energy and potential energy of the electron, which we do in a normal way is half mv square, and m1 m2 by or e1 e2 by r, or whatever it is, that e1 e2 by r is still there in this also, but the method of calculating changes now, because this electron doesn't believe in having a single form, right? It's like your Aperture style. It can be a wave, it can be electron, depending on, right, your Remo or Aperture Ramo, whatever it is, kind of thing. It has a dual nature, right? So that is what it does. So that is the reason why our life has become a little bit complicated. At the same time, actually very interesting. In fact, if you look at the history, the maximum number of Nobel Prizes came in development of this field. Right from your Einstein, Planck, Bohr, Dirac, all these people are, I had to worship them every day, because I got my job because of those people, right? Because I did my PhD in that, and then I became a worker in that because of these people. Terrific job, most of them. Malikian, for your MO theory, Pauling for your valence bond theory. These two are different. Imagining your molecules, trying to tell you how the molecules are sitting. You didn't even think of that. You said oxygen is there, hydrogen is there. Today, if I say water molecule, right from school, child says HOH, right? And then the angle is told you how that VSC par theory or water theory. There are hundreds of theories which tell you how the angle comes. But these are the demigods or semigods who have told us how to do it. And today, if I have to imagine that, it's because of this. So that wave equation, which I will tell you, was put forward by Schrodinger based on those things earlier. It's called Schrodinger equation, which all of you know. It has a form, Hamiltonian, which is not something new in quantum mechanics. Hamiltonian is something which comes from classical mechanics anyway. You have heard of Newton's law, F equal to ma, one of the most famous laws. It's called Newton's law. The same Newton's law can be put in another form. It is called Lagrangian form, which has L. People, we don't learn that. I do not know if anyone has been thought about that. The same thing, except that Newton's laws are not easy. In some conditions we cannot solve it, because we are not looking at simple throwing the ball and catching it all the time, right? In classical mechanics, you have huge things which you have to calculate, right? At that time, Lagrangian is easier. And there is that is the energy form of that. This is force form. F equal to ma is a force form. Lagrangian is energy form. Hamiltonian is also energy form. There are three equal methods in classical mechanics. They are Newton, Lagrangian, and Hamiltonian. This is from classical mechanics. So based on this, our chap did that and the wave theory, and he combined it to give you what is called the Schrodinger equation. He said, since there is a wave format, h psi equal to E psi. That's all. There came a school which came much later, which was called the modern quantum mechanics, which is based on postulates. And that is a better method of understanding quantum mechanics. It says the wave function represents everything about a subatomic particle. And you must have read this, right? Many of you. Postulates of quantum mechanics. Read it and then forget it. How many postulates? Anyone can sit with the cell and find out now. 2 minutes. Google. That's There's so many postulates, and if you remember the modern quantum mechanics, you don't have to worry about Schrodinger equation. Modern quantum mechanics, just like Newton's laws, are postulates, and you accepted that. F equal ma, you accepted because you felt it is easier. You felt that action and reaction and all the third law and inertia. You imagined that, and you said that to accept. They're all postulates again. Same thing here. There are postulates. This is the old quantum mechanics where Schrodinger put the wave equation. Many people did not like it because it shows wave has weight. The 2m minus 1 by 2m thing, which they didn't like. So that is why you use that modern quantum mechanics. So you remember, you take your textbooks and start reading from the postulates and say, okay, I accept the postulates. Just like you accept 1 plus 2 equal to 3. Right? Start that. And then your quantum mechanics become beautiful. You'll start enjoying the subject. It'll look like not like an art movie, it'll look like a beautiful comedy or a romantic movie, which you'll enjoy, right? Not like an art movie where it is very boring. It will become very interesting. So this H, which is what I said here, this is all based on that. But you'll be still solving H equal to E, but that equation comes from modern quantum mechanics, where operator is given a form. It says operator, eigenvector, eigenvalue, eigenequation, right? Yes? And what is an eigenvalue? What is an eigenvalue? You have an operator operating on a vector to give you operates on eigenvector to give the eigenvalue, right? And the eigenvector remains. And there are cases where there is no eigenvalue equation, then you take the average. The postulate tells you so, right? Psi h psi, the average value, right? What is an eigenvalue equation? Simple thing, I'll tell you. I want to measure the length of this chair, top part. Okay? I want to measure the length of this top part. I have a scale. That is the operator. This is my eigenvector. I measure it. What is the value I get? I get the eigenvalues, which is the length of this. And what has happened? The chair did not get destroyed. Simple. I take a scale, I measure it, and I get the length of this. I get the eigenvalue, eigenvector remains. Now, I want to find out the heat of combustion of this chair. What do? Burn it. I've destroyed it, but I get the value. So that is not an eigenvalue equation. Simple, is it? Is it not simple? Yes or no? That's all. That's what you're doing with this. You're measuring the energy. You're taking the wave function and measuring the energy. That's all we're doing. Okay. So now, having said something about the molecule's energy, we are now looking at what is the thing which we are studying. In your Gaussian or software, whatever you're running, you are running it and getting the energy of an isolated system in atomic units. But really, in reality, even if you think of an internal energy of a system in a box, it will not be one molecule. So we have to talk about, as chemists, in terms of moles, right? So what do? We have a lot of molecules inside, and that is what you are doing, the total energy of that system with a lot of molecules inside. But energy of each one is same here. When we neglect the interactions between this, and that is what we call the ideal gas situation. PV equal to RT, no interactions. We're talking about interactions in that. So here we don't have interactions. There is no interactions with this. So we neglect the interactions. So if I have 6.023 into 10 to the power of 23 molecules, the energy will be of one molecule into that will give me the total energy of the system in kilocalories per mole. What you get is in atomic units, which is one molecule or one atom. But if you do it with multiply it with 6.023, which you don't have to do, it has to do it by itself and will give you in kilocalories per mole if you're looking at the difference of the energy. Here you will be neglecting the interactions between the molecules. Okay. So This is what I said just now. So we assume the molecules will be non-interacting. So at n into total of the electron energy of one molecule, and that gives you the total energy of the system with n 6.023 into the power of 23 molecules. Next, we only got that. What about the vibrational, rotation, and all that? You're learning statistical thermodynamics, right? Partition constant, at least the chemistry, what telling about partition constant and all that. What does it mean? At room temperature, electronic energy is very safe. All are at ground level. As chemists, we know what is ground state and excited state, right? There's something called ground state. In the electronic energy at this temperature, everything is in the ground state. So there is no problem. So you are only looking at the energy of that. But when it comes to vibrational and rotational, the gaps are small. Energy levels are between the levels are so small that some of them are populated even at the room temperature. Rotational much more, and translational really all. Yes. So we use statistical thermodynamics to calculate that Boltzmann distribution. And also one thing which you'll learn in vibration, what is that? At zero, n equal to 0, there's still energy, that is half h nu. Learn that, right? N plus half h nu is the harmonic oscillators 0 point energy. Exactly, ZPE. And what is that ZPE here? When n equal to 0 is half h nu. So that is added to the electronic energy. So you have calculated the electronic energy, which I was talking about. Then you can add ZPE to add only the vibration energy, or you can add even rotational and all that using the partition function, which you don't have to do. There are things in the software which does for you. So electronic energy plus your vibration energy, vibration energy and any of the other, depending on that. So you know why you are reading all those now, the partition function and all that stuff. So technically you will have the total energy as translational, rotational, vibrational, electronic. And if you add the 0 point energy and also put the temperature, you get the enthalpy, because we were talking about only internal energy all the time. But we in thermodynamics know there is nothing. We have E, H, and H is enthalpy. What is the higher next form? Higher form? Energy? Free energy. G. Right? Yeah. Gibbs free energy, more specific. So H, G. So you will get all these in your output. So remember, you are doing your thermodynamics. You can stop with internal energy and do your calculation, or you can do with enthalpy and do your calculations, or you can go even to free energy. And also taking into consideration the temperature. So at that temperature, the partition function, it says how much vibration is populated, how much rotation is populated. Luckily for you, the program does everything automatic. Only you should know it is doing it for you, right? Okay. Anyway, that's the same thing which. So anyway, this is something which again, it's not just I had this Gaussian zero, and what's your version? 1.6. That's the last one, is it? They don't have 20. Latest is 16. 16, okay. 16W or 16 you have taken? HP, okay. Okay. Okay, this is some old slide. So it's not limited to Gaussian. Gaussian is like, again, I'm trying to tell you, it is one of your top softwares. But those who want can also look into all this, where the last two are even free softwares. You can publish, but you know, there is a difference between Gaussian and this. Gaussian makes your life definitely easier. I mean, when you're working on it, you will know. Even people like me, okay, let me put it this way. When there was a problem with US in 90s, there was a sanctions, and they said no Gaussian software to be sold to India. At that time, luckily for us, there are some Americans who wanted to help us, and they had this game as US UK, and I was able to get that software. Then the calculation is same. Let us say, first there are some limited things like it's not going to have a lot of features. Some features are definitely less in the free software, no doubt about it. Why is he going to give you a cost for? There are features in that, but the one which we used, it was sufficient for us. We published a paper. With games. Yes, we had done that. It's not unpublishable, but you are definitely going to take more time. Not exactly. The analogy is not good, but let me put an analogy. You take a knife and start cutting the weeds, or you have a what do you call automatic weed picking up system, which would be preferable, which will be faster, right? But if your area is small, right, even knife is okay, right? So looking at a small molecule, am I making myself clear? Have I put half of you to sleep? You had tea, right? And then, so that analogy is okay. If you have a very small patch, knife is also okay instead of using the automatic machine. But if I have a whole big room, which big molecules or something which more features, then I would like to do with the automatic version. That is what here. Pardon me? Like I said, some features are going to be definitely absent. If you're looking at only energy of a molecule, you want to find out some simple binding thing, and all that the games will do it for you. But Gaussian has much more, like molecular properties and all that. It is much more. Definitely, they are. In fact, what happens is it's like your when Unix system came out, what happened? They said people are making money out of it, right? Then Linux brought out Linux systems. Linux is supposed to be free, right? Or simple. I think you know that, right? Similar kind of thing. People did not, they said they're making money and all that. But that is not exactly, there are extra features. If you, ADF is not as costly as Gaussian, but quite tough this. And I have limited this here. There's so many of them. Today, if I go through there, if you Google it now, ab initio softwares, you call them ab initio softwares, you can get more than what the. What the accuracy of Orca, I do not know about that. Who is, which is the school? Again, yeah. Before you look at that, you should know which institute or school is offering you that. Right? If I were to tell you that this crocin comes from China, would you have it? I'm sure you'll not touch it. If it comes from Switzerland or India, yes or no? Yes, right? So this is important. I do not know about Orca. Frankly, I'm not saying anything negative about it. Right? I have heard of this program. Then definitely there is something. But what I'm trying to say is, please go into the actual people who are releasing that software, who have good publications, and that too publications in which journal? ACS, Royal Society, which are peer reviewed, not in Betham or whatever. There are so many of those local journals which I would not advise that. They're quite good. They're quite good. They're quite good. Accuracy is good. If you're looking at energy of a molecule, I get the same value. I have used all that. I used NWKM. I have used ADF. I have used Gaussian. ADF is a slightly different software. It's called density function. That is not going to let put more details here. Density function. Okay, all this. And some run on Windows PC and some need high performance computers, but high performance computers means faster. Okay, but you are calculating H equal to E psi. That's our thing. Again, like I said, This is wave function. ADF is density. It is density. We don't have enough time in this 1 hour or whatever it is to go into so much depth. Okay. Now, yeah. Gaussian is good. Yeah, definitely better. If you want to use a longer, pardon me? But then it depends on the nature of your problem. If your laptop can handle such a big that is definitely. You see, the limitations are always to be taken care of. Laptop can take up to a certain extent, but it cannot go beyond that. Otherwise, rival servers exist. If everything can, but today the laptop cannot do what. But again, polymer, if you want dye or fry. Yeah, metals you can. No, all the metals, not radioactive and all that may not be there. Again, parameterization of that. The common metals like your, what is that? Your transition metals and all that can be taken. They are there very much. So as you go along, you will know the limitations and the, what you call, the flexibility of these programs. Like I said, laptop is not a replacement for your server. And also if your polymer is only 2 units, maybe you can run it on a laptop. But if you're going for 6 or 7, then right, then you are going to be stuck because your RAM and all that is not going to be sufficient. It depends on not the number of electrons alone. Again, depends on your model there. The model is, I really did not bring that. Okay, yeah, I'm sorry. That is a slide I'm having here. Okay, Huckel theory, which you learn in your chemistry, right? You know, Huckel theory. What does it do? It neglects all the sigma electrons. That is here, Huckel theory. Only pi orbitals. Then extended Huckel comes with it. What is that interaction of all that resonance integral and all that extra? So that comes to extended Huckel theory. That is also there. These two work for your spectroscopy. They are still good, right? But you cannot use it now for something else. They're still good. Then semi-empirical methods. What I showed PM3. Maybe you do not know much about it. It's called PM3, AM1, and so many of them are there. They're called semi-empirical methods. Maybe once you're going into the depth, you will know that also. That is also quite fast. So if I take a benzene molecule and do a Huckel theory, it is over in seconds. I can do it with the hand. I don't have to use a computer. Extended Huckel takes another few seconds extra. Semi-empirical takes less than a minute. But it does. It also does some approximation. But then comes the ab initio density functional, where it takes more time. That means it takes into consideration all the 6 into 6 electrons of the carbons and the hydrogens, everything into. Remember that Huckel theory took only pi electrons only, but where here the total number of electrons are much more. So you expect much better, right? And the approximations and all this. So there are so many of that. Like I said, this is not a quantum mechanics class, it's only introduction of computational chemistry. But maybe if you go into those textbooks or the next few days in the workshop, you may be able to, if you are not limited to Srinivasan, if you're not limited to only ab initio. Is there. If you're not maybe semi-empirical also, if they see, they will understand this. Because many of them may be sufficient also, PM3 or AM1, that also is. Okay. And then ab initio. Of course, this I showed is because the next thing which is towering up is AI. It's taking up all this. By the time we start learning this, AI is coming to the picture, coming into with doing all that. In fact, we started that in IICT. Unfortunately, COVID was there. Otherwise, our plan was to start AI programs to predict the properties. And it's still, some work is going on using quantum mechanics and all that. So, machine learning, AI, ML is part of AI. That is true. That is okay. Okay, now we come to the real one example. After this, I'll give you 2 examples. One where now we're coming to the actual research work. For those who slept because of the basics, this may be a little more of something which came into publication. An industrial problem. Something quite interesting because it has to do something with ISRO, which is now the Chiranjeevi of your science today, right? ISR is a catchy. Chandrayaan and all, everyone has. Okay, we are talking about quite some time ago when, you know, the rocket nozzles, believe me, these are not something which I have worked on. I'm only showing it from the internet because we have worked on the specific problem with the VSSC people. That is real. But if I have to show something to you, I have to bring something from net also, right? This is the rocket nozzle and it is made out of a niobium hafnium titanium C103 alloy. And that requires these metals. Okay. Now, this Colombian alloy is a high temperature resistant alloy, which is in the nozzle. And it's alloy of what? Technology to produce this alloy itself is closely guarded. And in the world, only 1 or 2 advanced nations at that time could have had achieved it. I'm talking about a time when Madhav Nair and we, personally, even Madhav Nair, I had interacted. So I'm just talking about, but I'm only just trying to show you something, just simple words here. It was quite a close contact we had with ISRO. Okay. So ISRO successfully developed this alloy. Okay. Then came the Pokhran blast. Those who have heard of it, took place in 1998. There is movies on that, right? What is his name, that hero? Yeah, right, Parman. That is a movie. Though, for those who have not seen how it was covered and the Pokhran blast took place. When they came to know, the Americans got very upset and they said ban of export of certain defense and technology material from USA, which included Goshen also at that time. Goshen was also stopped. They said we are not going to give to India because we did something which they didn't like with that Pokhran blast. Okay. So at that time, what happened? ISRO buys hafnium from US. Now that is stuck up because they have stockpiled hafnium for the next 50 years because hafnium you need only in kilos and they have tons of it. And why should you do it when they are already having it? So our people were upset. So now they are not able to get hafnium. Now there is a factory in Hyderabad called NFC. You have heard of that nuclear fuel complex? No? When we were at your age, we did not have Google or to understand history and culture or the scientific developments. But with you people, I think you should be much more vigilant on this. Right? Understood what I meant? You people should be more knowledgeable. Don't Google it at that time. You should have known these things. Nuclear fuel complex is a big one in this country, which produces zirconium. Today you are celebrating the Chandrayaan there, but where did these things come from? Which included NFC also, the picture. Okay, and NFC has a zirconium which they are extracting, but they didn't bother about hafnium which comes with the zirconium. You know that zirconium and hafnium exist together, right? Chemistry. And what does it do? What was it doing? It was throwing that zirconium waste into the streams, and they are highly concentrated nitrate streams. And farmers around at that time we heard that how far it is true, we do not know. They were taking it because it's rich nitrogen, and they were using it for farms. It's very much possible, but anyway. Then the VSSA team came to us and said, kindly look into a procedure which we can separate hafnium from the zirconium sands. Okay, anyway, that is so what we did the literature survey for this. Okay, not many publications in the recent years because technology for hafnium zirconium is something even before I was born, it was known. So people did not bother about it. And established role process and literature. So what are the existing process? MIBK, methyl isobutyl ketone, which extracts hafnium selectively into the organic solvent. Again, another tributyl phosphate process where the TBP is extracted. Those who know about extraction, they are nothing but chelating agents catching the particular metal specifically and pulling it out, right? It's specifically catching the particular metal and pulling it out. And third one, Sezu's process, which is not something of important, but it was electrochemical process. We found there were 3 processes in the literature, and we wanted to, they gave the project to us, VSSC, they said, you look for a new methodology, and they gave the project to CMET, which is Department of Atomic Energy Scientific Institute again, and they were asked to standardize tributyl phosphate method. Okay, are you with me? PPP and MIBK process, these are the things. Now, we chose, why don't we look for macrocyclic ligands? Because we don't have to dirty our hands. We have computers. You only have to draw the molecule and start looking at that. So what did we do? Why not macrocyclic ligands? Because we found out that in literature, this is one example where separation of metals, the TODGA, when it is added, you are doing that extractant. You see, it does specific extraction because of this. And similar kind of thing here. This is another extractant which has, for trivalent actinide and lanthanide extractants, it is picking up specifically those. What they found, the solvent extraction here is 5 × 10⁻⁵. I just showed you one, just to make myself clear again, an example of how the solvent extraction is taking place here, which is nothing but oxygen atoms picking up the metal. And here I am talking about specific metal complexes here, like actinide and lanthanide extractants, using this molecule for extraction with different R2 and R3 groups. I'm not going to depth of that. What happened was they found that this comes from a big Oak Ridge Institute from US. They found using calculations that this one, the structural reorganization of this molecule, which is here, when you look at it, you see that these vectors are separated out. And if you bring them together, then your extraction will be better. Theoretical calculations of that molecule. They found theoretically that if you bring the 2 oxygen atoms, though it looks here that they are close by, here if you bring them together, the extraction is better. And what did they say? They designed a molecule of that kind. What has it done? It has frozen the oxygen atom's direction. Okay. Should I repeat that once again, or you understood that part? Oxygen atoms are in that molecule like this, which can pick up the metal, right? But that is flexible. That so it can rotate as it likes. So the efficiency of extraction was not good. So what did they say? They said if you make it this way, the extraction is going to be very good. By theoretical calculations, they found that the direction of this, and they froze this by putting the rings which freeze the direction. And what did it do? It gave a how much? 500 times more extraction than the other. See the wonders it has done. Simple calculation showed them that. So this became our kind of motivation. So we said, let us look at the MIBK process. What did we see in the MIBK process? We found that zirconium chloride, tetrachloride, and hafnium tetrachloride are used, and specifically the in the methyl isobutyl ketone, and this is water. Specifically in this part, the hafnium goes into that part, into the organic solvent part. Okay. But that we found was by adding thiocyanate. That is what the process does. You have to add thiocyanate ions for such a thing to take place. So what is the role of thiocyanate ions? So we thought we should check that first to tell our people. And once we know that principle, we can actually do the macrocyclic ligand. So what did we do? We found out here we did ADS software anyway. This is just nothing different from your Gaussian. And we use the internal energy model of that. Complex energy is calculated. And the solvent molecules, you can use it like this. You can have water molecules separately, what we call the explicit solvent molecule, or you're taking the field, which is called implicit. This is just more simple ones. Okay. Here we found, yeah. You will not, yeah, you cannot. You have to only put as much as, yeah. That's what I'm showing here. In fact, that's a good question. So you have two types of ligand interactions. You have the metal, which is now with tetrachloride. Let us say tetrachloride. How the water molecules are interacting when I have two here. It can have the equatorial type or it can have the angle type, right? Then you can have 4 water molecules. So trial and error. That is what we did. You can, yeah, it's like more explicit. Like I said, explicit. We have to do that. You have 4 water molecules. You have these two possibilities, the structures. Okay. And then we do what is called geometry optimization, which we'll be doing tomorrow, which or today, whatever it is. One thing I should tell you, other than energy, the most important thing is the geometry. You cannot take the energy of a molecule which is having, let us say, HOH. Let us say, simple example. I can have a OH bond at 3 angstroms and one at 0.9 angstroms. That doesn't make a water molecule, right? Because this is 3, the bond length. It can still exist as per our calculations, but it is not that thing. So we had to do what is called the optimization, which means the correct geometry as per our model, which is 0.9, 0.9 or 1.0 or 1.0. And once we come to that, we learned this. I don't have the blackboard, right? You have the potential energy curve like this. You have learned that, right? Yeah, local. You have normally even you don't have to go up to optimization. You have the potential energy curve which you learn in that it comes down, and the bottom part is called the main geometry. As they come closer, the repulsion energy increases. They go far away, they start breaking, right? So that potential energy depth, that is what we are talking about, optimization. Yeah. So we did that with for the 4 molecules and this one. But what we did, we used along with chlorides only when SCN is also added, and we found also with 4 water molecules. Anyway, these are the geometries. Let us not go into depth of that. And also with the acetone molecules, which means it's representing the MIBK. MIBK is methyl isobutyl. Now, isobutyl ketone and methyl, if I put 2 methyl groups for calculations, is okay. Isobutyl is going to make my life a little bit tough in calculations. So I change it into methyls. These are the models which we work with. You have to always define your model, stick to that model, and defend your model. Right? You have an extractant which is one side methyl, the other side isobutyl ketone. Okay? But if I say both are methyls, for my calculation, that's not going to make a difference. The isobutyl is put in the experiment for what? That is because it gives more, what do you call, solubility. So all those are for that. For us, it doesn't matter theoretically. So what I did was, I put this SCN NCS and did this calculation and got the energies of hafnium and zirconium with, in this case, with thiocyanate and water molecules. And what I want to make you observe here, if you do not understand the rest of it also, you will find that the with the thiocyanate, the hafnium is 102 kilocalories and this is 91 kilocalories per mole binding. Which means if I go again, whatever angle I look, whatever thiocyanate or NCS I put, whatever chloride or this the other what is the molecule there here? The methyl isobutyl ketone or dimethyl MIBK is equivalent. I am always getting the hafnium to be more stable, which means if I look at this, hafnium is always the delta delta E, which means difference between these two. I find for whatever configuration I take, that hafnium is more stable. Only when you put thiocyanate. Without thiocyanate, they don't give that much energy. So if a simple chloride is there, I hardly have 5.98. But with the thiocyanate, it becomes almost 2 to 3 times more. So that is the reason for why thiocyanate is added. And we found that with different structures, 19, 2.4 to 5.5. And we showed that when you look at it, always that hafnium is binding better to the solvent when thiocyanate is added. This is what we have done, and we told the experimentalists that to design a macrocyclic ligands, but add thiocyanate, and then it is going to bind better to the hafnium and separate hafnium and zirconium. The experiment worked, but in chloroform. And your industry process is in kerosene. So unfortunately, we couldn't proceed, but it was a new work. So VSSC were very happy when we put it into JPC, Journal of Physical Chemistry. That was good. And CMET was already taking the established procedure. We said new procedure. We were able to give knowledge base. We tell that, right? It's not always you come out with something innovative. The Chandrayaan 2 did not land there, right? Or 1, whatever it is. It came up to that part. So that's the knowledge base. And then, so we told that part, and that is that preferential extraction is done only with thiocyanates added. And as the story goes, at that time, it was interesting, which is, I don't know how far true. We came to know that Americans, though they put the sanctions, they want to still sell the hafnium. So through Singapore, they were smuggling it and selling it to India. So, but luckily, Make in India and all that stuff our people got, and CMET is now producing hafnium. This is a story which we had a very close collaboration with VSSC, and particularly, like I said, Madhav Nair himself was interacting with us, and this is a story of that project where we did. Yeah. No, this we used the cluster, yeah. But we were able to do some of that. I didn't bring those examples because there's no limit to that. And I'll tell you one more example. I think I am, wow. I may need some water, I think. Yeah, time is there, but my attention is running out. I'm not seeing anyone interacting. I'll just give another 5 minutes. Sir, yes, sir. Where it is? They are not interacting. We agree. Yeah.
Exactly the quantum dots recent.
But what do you want to do? That is more important. You can, these are big words, words. Going from bulk to the you need a bigger Gaussian order limitation for that. And it uses instead of you see our Gaussian actually what is your actual form of you said hydrogen orbitals are difficult, and you've made it into what is called the what is that orbital? Slater's orbital, STO. You will learn that, right? STO, you start generating orbitals. That is slightly better than hydrogen because you can do the calculation. But even that is worse. You said it is better to use Gaussian orbitals. Trying to think of the wave which we have, H psi equal to E psi, do not know how the psi is. Actually, we have solved this only for hydrogen atom, reality. But that is not the case because hydrogen atom doesn't have interactions between the electrons. It has only one electron, right? It is like your sun and earth system. But that orbitals we decide is for everything. So, that is different. Then you can, but then VASP is also, all those are DFT. But what you do is when you go to still higher systems, you use plane waves, e to the power of IKR. You don't use e to the power of alpha r square or alpha r minus alpha r. You're doing IKR. That is your plane wave. Plane wave does calculations even better. VASP is there. So many are there. I think Expressa is there. That's right. And one more I keep forgetting. CASTEP. gas step is there. So many other, right? So many other. I mean, suddenly. So those may be better once you start talking about solid state. Okay, so this is one application for industrial thing, and one more before you people say stop, I should stop. So I don't want to talk about this TaO2 thing. In fact, this is here that is the cast up thing where we have the DOS. You see, which comes out. Let us not go into those details in this. Okay. Another important, just one more thing, which I want to tell you. Okay. A simple idea. One of my students, when we were working on nonlinear optics, said, "Sir, there's a paper which came in Physical Review Letters. They had, in fact, this is a JAX paper much later, where they were doing the gamma, which means a nonlinear optical parameter, one of them. And what was interesting is this molecule has a absorption at 1100 nanometers. Solution phase, 1100 nanometers is like near infrared, you call it NIR dye. And then he said, sir, why don't we do calculations on this? Okay, this is the reaction. For those organic people, they can enjoy it, but this is the actual molecule. So they said, why not we do it? We decided to start on that. We found a similar kind of molecule, squarene croconides. Same substitution. You have heard of these molecules, I'm sure of it, right? Same substitutions, we find that croconides always have 100 nanometers redshifted. The same substitutions, like if I have this heterocyclic rings here, this is 713 and this is 845 nanometers, 804, 950. And as you go to tellurium, the selenium, tellurium and all that, it goes to 910 to 1081. Okay. And one more interesting thing with this was someone did calculate, they said, okay, if I extend the conjugation of this molecule, it should even absorb better, right? Simple logic, 900 nanometers. Okay, you extend the conjugation. But what they found is as they increase the conjugation, it dropped. Now, more interesting thing there is someone explained Nanguchem, again, something which you have to realize that. What is it? Highlights. He said, this is having 2 plus positive and this is 3 plus inside the ring. So this acts as a super acceptor. So one thing which I have to tell you that don't accept it blindly because we did calculations and showed that was wrong. Anyway, that's, we are not going into depth, but when he explained that, it came in Nanguchem highlights. Nanguchem is something big, right? Am I making sense? Okay, very few PhD scholars are here. That's true. It's a big journal anyway. It's a big journal, and we were struggling. So then, what did we do? We said we should do calculations on this. I won't take much time in that. We said if it is DAD, why not we look at really what the donor acceptor thing is. As we said, why not we do it in the calculation? Because calculations can do anything, right? So we started looking at the charge transfer. And what we did was we took a model molecule oxyallyl and then the squarene and croconate. And we found that actually there is not much change in charge transfer. So what Langle said that the 3 plus ring in this and 2 plus is not showing it in actual calculations. You change the groups. In fact, if I change the groups to even bigger real groups here, and for squarates and for croconides, I find the gain and loss of electrons, which is again a theoretical study only because experimentally you cannot measure the charge on residing on an atom in a molecule. And I still find, for example, I take this last molecule, I find the total change in the, minus 0.04 on the ring oxygens. Central ring is 0.10 and minus 0.06 in the R groups. And I go to the croconate, I find there's not much difference. So that means Langels is wrong. What he said was there's 2 positive, 3 positive, and it is a large donor acceptor complex. We found it was wrong. So we did our own calculations. I'm not going into the details. And we found out this is simple molecular orbitals, simple MO, right? This comes out in your output. I look at the HOMO of this and the LUMO here. When I bring these two together, there is a stabilization of the HOMO. When I bring these two together, there's a stabilization of the HOMO, it is coming down. And because of that, there's a destabilization of the LUMO, it goes up. And the similar case, when I take them away, they're coming closer, orbitals. You can see this picture clearly. It's not a major thing. These are the HOMO and the LUMO, which I'm sure many of you know what a HOMO and LUMO is. And I find that these are, when I bring the orbitals together, which means in this molecule, since the distance is larger, the HOMO-LUMO gap is going to be smaller. Okay, simple molecular orbitals we found that. And squarene is because of it. And we showed there is another molecule with 6-membered ring, which will be even further redshifted. Simple idea brought down by one of my students, gave rise to 40 to 50 publications in all beautiful journals and some 3-4 projects. And still some of my students in NIT and Nanded are working on this. It's a fantastic thing what a simple idea has given us. So I do not know whether I made myself clear here. That is what I wanted to. I think this is, so it is only a molecular orbital thing, simple. We just drew the molecular orbital. Angles came with some big ideas, but when angle came, but this is a simple idea of saying that there is a, when the orbitals are near, you know, the stabilization, destabilization, right? That's all. So I will stop with that because I think this molecular, this might be for something else. And OLED, maybe I took too much time in and if I go with all this, your lunch also will be okay. I finally wanted to end up this with what I liked in one of the things with Gaussian gives you as the end, it gives you some interesting kind of things like this. It'll be very nice. It says, in beginning, God made man, he worked dirt with his hands, and God decided to give man science. Man should be useful. Soon man's knowledge grew too great to the heading science he couldn't relate. So God said, let us have different fields. We'll divide them and see what it yields. So what happened? Science became physics, chemistry, bio, and they sprang around Nile. Okay, Egypt, Rome, and all that were the ones which all that. Experiment was God's decree, but experimented chemists with a lot of glee. They were very happy to do it, but soon the test began to bog and found themselves deep in a fog, confused. Give us some help, they cried to God. God looked around, then gave the nod. Enter Einstein, Heisenberg, Bohr. Reaction paths were clear once more. With theorists, God sent direction, and then he stopped. He made perfection. So it's a sort of, praising us as we are perfect people. So there's no development after that. Okay. So I should thank you for listening patiently and not, disturbing me in the middle, asking questions. Right. I'm open for any discussion now. I did want more information, but I think 45 minutes.
Really, thank you. It's a wonderful opportunity for us to listen your talk and about your thanks for sharing your experience about Gaussian. Definitely, it is a motivation for them to learn about the Gaussian. So where we can stop. Exactly, HOMO-LUMO and molecular orbitals, interaction energies, and the solvation model, implicit, explicit, everything you are going to learn for this today afternoon and also and whole day for tomorrow, and even including the transition state, all those, and including that crystal structure, how to make that optimization and compare with the crystal structure comparisons. Those things we are going to do that. And okay, before that, that is a afternoon and tomorrow session. It's usually the quantum mechanics on the Gaussian is Dirac said everything you just put it into that in the equations and solve it, definitely we'll get some kind of solutions. So likely that Gaussian came to us. And Bhanuk Prakash sir is wonderfully explained each and every component and share his experience. Now that time for question answer. Students, it is essential, and also the participants, please put forward the questions. What if you have any doubt or any kind of thoughts? It's not necessarily only the questions. You can put forward a thought also on this spot. Is open for Q&A.
Sir, actually, I have one question. You remind me that when the cyclization occurs, the pi conjugation increases and absorbs in NIR region. In fact, we published in 2010 when I was in Tokyo, Professor Hiroshi Nishihara group, similar kind of things. And still I have one unsolved theory, would not able to understand why. Maybe I can discuss with you later. And when we have 6-member ring, stabilizing oxygen 6-member ring in aromatic is very, very tough. Then we have done at the time by attaching some donor, strong donor like triarylamine, we have stabilized. Still such kind of examples I could not able to see in the literature. So that time they appreciated, Jack's people appreciated the paper, and later on we try to do the same way with the different things that could not be able to do the things. That is very unique way to do that. And as we said, we can always differentiate the 5-membered, 4-membered, 6-membered ring by attaching the donor. And of course, a 6-membered ring, it can able to still go further in NIR region.
Don't worry about the
Yeah.
I didn't show you that the conjugation changes the orbital pattern. HOMO and LEMO now change. So that theory, that's it comes down.
Yes, yes.
The conjugation is separating the.
So actually, that time we have used anthraquinone moiety, and later on cyclization, it remembered the 5-membered ring, a kind of cluster 5-membered ring. Maybe I can discuss with you later that example. So thank you, sir, enlightening about the topic. Yeah.
So there is another question.
Sir, how can we calculate the Delhi energy of the optimized crystal structure? You present the optimized crystal structure energy Delhi value, right? Delhi. Yes, sir. How can we predict that value? But the whole structure value, we can estimate only the, for example, carbon-carbon in bond length value. So you can put the Delhi value, total crystal structure, positional orientation like that. Oh, okay. Okay. Okay.
Sometimes you might have to do it yourself. Yeah, sorry. Optimization is like you have a large molecule. Obviously, there's too many permutations, combinations of, you may have a full dimer, you may have a linear version, or you may have a helix, whatever it is. Optimization routines are there, but they're not too efficient, but many times we depend on that. Sometimes we do it ourselves, which it has missed.
Okay.
So that for water molecules, obviously you don't have any other, there's only one possibility.
Okay,
But
okay.
when you go to a foldamer or you go to a larger molecule, you have too many possibilities. As
But
people saying polymer,
we can some deviation based on the XRD value.
right? But that is again, you have to observe that most of your systems are not in crystal structure, right? You will be always having them in solvent or in gas phase or whatever it is. Crystal structure also is something of a different thing from the real molecule.
Okay.
Yeah, other molecules have packed it into that. So if you are looking for crystal structure, it is one method.
Okay.
The other is you may have a foldamer, maybe in a crystal structure slightly different from its free form.
Yes.
And free form may have something which is even more energetic than this. So there, obviously, it is not what you call automatic.
Okay.
That is where your chemistry, the person sitting there has to understand what he's doing. It's not a black box. I don't expect a commerce student to sit. I hope there are no commerce students here. Pharmaceutical, no. Commerce. Pharmaceutical, they're bigger than chemistry people. They do big things. Medicinal chemistry is part of your this one, right? This is organic chemistry, nothing but we have been teaching statistical thermodynamics and NIPER for many years. I have taught them. NIPER, pharmaceutical chemistry, they have medicinal chemistry. And I was teaching them statistical thermodynamics. So I'm not about pharmaceutical, commerce student.
Okay.
Why I'm telling you this example? When the fashion started about bioinformatics, I don't know whether you have heard of this word, bioinformatics. In 90s, every fellow was sitting with a internet cafe kind of thing and saying bioinformatics taught here. And they were calling us to teach. And one of the fellows was asking, what is R&S? Then I asked, what is your background? He said, I am some BTech in electronic. How are you going to understand what I'm trying to tell you here? This is chemistry. You should have some commerce student also, in fact.
Okay.
Chemistry, physics, yes. Okay, pharmaceutical is under chemistry, so nothing different. Biochemistry, all are under chemistry. I'm not talking about commerce, and you do not know what a fault number is, what this one is, what R is, what is S is. So then difficult. Your chemistry knowledge is important. Let me tell you that. You are chemist in that sense. The Gaussian is a chemistry software and also to a large extent physics.
Okay.
Okay.
Yes.
So you should use your discretion. Otherwise, what the point in sitting there and just giving the food, it will publish the paper itself. What is that? Chat GPT kind of stuff, right? No. Chat GPT do Gaussian,
Yes.
write the paper, send it to JAX. Over.
Yes.
Your life is easy, right? You use Chat GPT? Not yet. Thanks. So we don't go to that. Our chemistry is important. So you should know whether it is feasible. Sometimes, rarely, it can give you a structure which can never exist. I had a unique opportunity of getting benzene twisted in one particular software.
Yes.
Which is not possible. So you have to be careful. Not always, it doesn't happen always. You're trying something and it happened. You should be able to use your chemistry knowledge and interact with it. Okay. So please be careful. Yeah.
Thank you, sir.
Yeah, that's what I was just telling him. I didn't put that part. Actually, as I said, the molecular orbitals of oxyallyl, there's one, I showed you the bonding and anti-bonding, right? When you increase the conjugation, that molecular orbitals nature changes. So no longer it is the molecular orbital shift to the donor acceptor side. And the ring is no longer having oxyallyl nature. If only when you have the oxyallyl nature, you have the homo-lumo gap, which will go to higher, like rhodesonite, squarate, proconate, rhodesonate. But if you increase the conjugation, oxyallyl nature is changing. At that time, it becomes more of a simple, what you call conjugated system, so it drops down.
Excuse me, sir. One more. Thank you for explaining the DFT software behind the theory, sir. I have one doubt. You have mentioned in the slide, if you have the more distance, then the homo-lumo value will be small. You have mentioned in one
Yeah,
slide.
in that particular case.
Right? Yes, sir. From that, in that theory, the homo-lumo value should be small or should not be more.
No, like I did not put the real orbitals thing. Now you have two bonding orbitals. These are two bonding orbitals. Bonding orbitals. Yes. We know the two bonding orbitals are near each other. Let's step in. Right? Let's put them far away.
Okay.
Right? Bonding orbitals, not antibonding. They're coming close to each other. They become step-like. Okay. But now the antibond, when the geometry of the molecule is changing, the antibond will also come. So that is destabilized. So when you bring them near each other, the antibond is destabilized. The bond step, the delta E of the structure increase. When you bring them too far away,
Okay.
then what happens? The bond destabilized. It's going up.
Okay.
The antibonding is stabilizing.
Okay.
When they take a square which is 4 dimensional,
Okay. Okay, sir. Thank you. Sir, one more. Um, in what purpose we are using DFT? Because the homo lumo values, in case you are asking in a PhD defense, in case supervisor or something, the external asking in a PhD defense, in what purpose are you using DFT or a homo lumo means, what we can predict that? Okay. Thank you, sir. Okay. Thank you so much, sir.
Good afternoon, sir. Sir, could you please tell me the polarizability of a polarizability, sir? Could you, NLO. Could you please tell about polarizability? Why we do polarizability in DFT?
Polarization. That's what we do. It's called non-linear optics. Oh, thank you. That's what we do in nonlinear optics. We give electric field to the molecule. So many of these are there. You don't have to do only molecule. You have electric field. You can put water. You can put quadratic electric field and all that. These questions will come only when you start. We are looking at. You are going to drive a car. I have told you what all the car is, features, and how to do the driving. But driving actually, when a pedestrian is coming, how to do is your, something which you have to do only by experience. But polarizability is we did nonlinear optics. We published quite a lot of papers which keep the electric field, find out how the molecule is distorting the molecular density, electron density, and get that. But that's slightly higher, and you have to. Any other thing? No? Everything is clear? I can go happy back to Hyderabad that everyone has been happy.
Maybe sir will give them one question paper by
That would be good.
Take 10 minutes. Any other questions from the participants? Students, fine. Yeah. We can only show 2 dimensions. This 2 dimensions. Why is that? All the 3 are there.
Any questions from the PG students?
How do you distinguish them?
First of all, have you listened or you slept?
No, some of them were sleeping, but luckily they were not snoring.
Secondary particularly known as.
So actually, sir, in curriculum, we have incorporated the document studies and theoretical. One paper, full paper is there. The university is the first university to start this.
Oh, very
So
good.
we should thank to Deskan sir also.
So then it is good that you
And,
have people who are teaching.
Because in the future is going to be like that. No, wherever, whatever the computational chemistry is very important place, important role. Even if you join in a pharmaceutical company also. Okay. So and try to learn next 2.5 days. Okay. And of course, the theory plays a important role, but even if you don't learn theory also, you can have training in computational.
One thing I want to caution that is there are people who try to use it as real black box and then make mistakes of telling wrong results in places in public, which is a little bit embarrassing. Like I know people have. So that I think is, I would tell you to understand what you're doing. You may not be, you don't have to derive quantum mechanics, Schrodinger equation, or we don't do that. But if you do not know what to interpret or how to interpret, then you will be the laughing stock in the, because science is public. When you do science, it goes to public forum, whether it is your, what do you call, seminars or publications. You should not become a laughing stock. You should understand it. It's not difficult. You put your, and you have bright people like this who can take you in the direction.
So basically, you should have understand only the basic concept only,
Yeah.
and of course, later on only in the training session, you are going to know a clear picture. So what exactly the theory behind in this calculation, you should understand from this talk. And of course, in a couple of minutes, another sir is going to join. Please bear with another 1 hour. I know it, all of you are hungry. Okay, not angry, hungry, all of you. Later on, we are going to leave. We are going to give break for the lunch, and later on, you can directly join pharmacy block. I think Sir will explain you where to join. Okay, please bear another 1 hour because DLV Prasad, unfortunately, little bit late is there, but anyhow,
He'll join.
he'll be joining. Thank
So,
you.
okay, if there is no more questions, we'll close the session and we'll thank the speaker for
Yeah,
your
once
wonderful talk about that. Please give the applause for him. Thank you, sir. So we'll just give a short break, 5 minutes. Please take.
No break. Please, that means everybody leaves. No, please stay there. No break. Sorry for that. And
Then fine. Start.
You're forgetting everything. See, that's what.
Order actually is in.
Hello. Yes. Professor Prasad.
Yeah.
Am I
Hello,
audible
am
to
I
you?
audible? Yeah, I could hear from the program. Yeah, this is
Okay.
Prasad.
Okay, sir. Is it okay if you can turn on your camera?
Can I see?
Yeah, I can see you now. Actually, there are two cameras. That's why one of them is. Yeah, it will
Yeah,
come.
I could see the slides
Ah.
from the Department of Chemistry.
Just
And, there are some participants.
Thank
Yeah.
if you want, you can share your slides and we can start.
Sure.
It will automatically share. Don't. Ah.
Then only it will come on the screen. Right, sir.
Yes, fine.
I will do it very easy.
Yeah.
The slides visible?
Yes, sir. Yes, slides are visible.
Should I put in the full screen and therefore maybe more visible. Yeah. Hello.
Hello.
The slides.
Yeah.
Yeah. Are the slides?
Yeah. Yeah, we can see the slides, sir.
You can see the slides. Okay. Should
Yes.
I start presenting it?
Yeah. I just introduce you, sir. Then you can go ahead, sir.
It's okay. I
So,
think it's
hello,
already-
participants. Yeah, is it okay, sir? We can see your
That's-
slides and as well as we can hear you, sir.
Sure. Okay. Thank you.
Okay. Yeah. So
Yeah,
here is the next speaker.
participants,
The talk is in online. So is a Dr. VLK Prasad. He's from IIT Kanpur. He's a professor actually. He did his PhD from University of Hyderabad, and later on he did couple of postdocs and joined IIT Kanpur as assistant professor in 2013. Later on, he is now actually professor. So he'll be giving his talk, and his title of the talk is Atoms, Molecules, and Photons, Simulations, and Uncertainties. So we'll be discussing on that. And I just request Professor Prasad to start the talk. So, sir, over to you.
Yeah, thank you. Excuse me for my delay a little bit. I have some other meetings.
No problem.
As usual, yeah, when you talk online, there will be some delays. So I thank the organizers and especially a good friend of mine, Professor Prabhakar, and as well as the Vignan and other organizers, and the one who introduced me to this presentation. Thank you all. As the convener introduced me to talk about on atoms, molecules, and photons, simulation and uncertainties in this workshop, I would like to take this opportunity to also highlight two of the Nobel Prizes given in this year. You could see in the chemistry, it was given to quantum dots. They're actually given from interaction of light and matter interactions. The other prize is given in physics to understand the chemical events at very fast chemical reactions, something like attoseconds. So there is some relevance to my talk today. I would like to put some basics in the beginning and then take you to forward the relevance of these in the simulations or in computational chemistry together. So what is a quantum dot? In particular, when you want to reduce the matter from macro scale to micro scale and micro scale to the nanoscale, one would tend to see the quantum confinements. In other words, what one would see is change in the electronic band gaps, and therefore you would see the change in the colors. I'm using the LED screens, for example, through laptops, and probably you are projecting on the LED screens the lecture. All that is due to the miniaturization of the chemical molecules or the quantum dots. That is to say, photons are nothing but light. So the light matter interactions, the matter here in the atomic scale, the atoms form together molecules and quantum dots. It's very rightly given in this prize, talking about the quantum dots that would generate the light with various wavelengths. The other prize is given in physics, also talking about how these electrons would react to atoms at a very short time length scales. As you could see on the screen, the electron that is moving much faster than the femtosecond. Femtosecond was known to chemists and physicists, but due to some technical advantages in the microscopy and engineering of the instrumentation, the scientists could able to come up with tracking the chemical events at the attosecond timescales, which is important to understand the real-time chemical reactions and their mechanisms. So with this background, I would like to talk about atoms, molecules, and photons in the perspective of simulations and uncertainties. I would like to talk about, in the beginning, atoms and then their interaction with photons or the vice versa, and talk about some molecules and materials, and then go through via simulations, and how careful one should do the simulations by understanding the uncertainties. So I spent a couple of minutes on this slide. I hope the audience would appreciate on this. As you could see, is this slide visible to all of you? The color and all? Probably. Hello? Am I audible?
Sir, you can see. Yes, sir.
Yeah, this can be seen. So what I'm showing here on this slide, you have a double x-axis. One is the length scale. It is shown here, centimeters. The other one is the energy scale, shown in the electron volts. But most of the time, chemists like to have in kilocalorie per mole. You can convert that into electron volt to kilocalorie per mole. That's like 23 kilocalorie per mole. But what I want to emphasize on this slide, for example, long ago, like 500 years BC, if you wanted to put it that way, the humankind is aware of the number of elementary particles in terms of few chemical molecules. So we were not aware of these molecules are constituted by the atoms, and then these are constituted by the electrons. So long ago, like 500 years BC, we are aware of few hundred molecules. Then we were thinking of these molecules constitutes the universe. That's like they are fundamental particles. Then moving on to the time scale and length scales, roughly about 1800 years, we know there exists an atom. That's like Dalton, right? Dalton proposes the atoms. These atoms would interact with light, which I will come back to you in a minute. And down the line, we also felt, no, atoms, yes, constitutes the matter, but it's more of electrons and the nuclei, particles, that all constitutes the matter and gives us the understanding of how the electrons and atoms would interact and form molecules and materials. Molecules, I also mean a small scale chemical molecules like benzene, or biological molecules of the order of DNA. So there is a length scale associated with it in terms of the number of atoms. As you could see, the endeavor in science allowed us to understand that's what I wanted to communicate through the slide. So we now know through quantum mechanics and beyond, there's a standard model which talks about the formation of the universe and its understanding. But what I would like to talk in today's lecture, I would like to talk about atoms and molecules and their interaction with light that we would only understand through the quantum theory, right? So long ago, I told you, Dalton has postulated the atomic theory. And then these atoms, when they scatter to the light, they generate the spectra, the electronic spectra. These lines, what I'm showing on this view graph, is not understandable than the existing theories. For example, we all know Newtonian mechanics. We don't have any idea of understanding the color, the placement of these lights and their excitations when the atoms, for example, hydrogen, sodium, potassium, are scattered to the light, right? So when such objects scatter to the light, one can generate and simulate that phenomena. One would call that when the heated bodies generate electromagnetic radiation, we get a spectra. In simple language, one could tell that it's a black body radiation. So what you could see on this slide, the dependency of the wavelength and the radiation intensity. The correlation between radiation intensity and the wavelength, people could not able to interpret and understand than the existing models. One has to understand the matter is constituted by the atoms, and these can be only explained by the quantum theory. When you place the quantum theory into the context, rightly so, people are able to understand the correlation between the wavelength and the radiation intensity. This has been summarized by an extensive model called Planck's model. Nowadays, we can call also quantum theory. That energy is directly proportional to the wavelength. That proportionality constant is called the Planck's constant. This is the original graph plotted by the very well-known Max Planck. So we understand this. People could able to put that in the perspective where we can understand the atoms and molecules and interactions, not by the Newton's of motions driven from the classical mechanics. I said it classical mechanics because the theory that is driven by the Planck quantization, in other words, we don't have the continuous phenomena, much like in the classical mechanics. Rather, the energy is quantized. That is what dictated by the quantum theory, right? All this has been summarized in a model called quantum mechanics, which I'll back to in a minute. The success of the quantum mechanics, as I showed you in this slide, it can allow us to understand the electromagnetic radiation, which I have shown you here on this slide, like the gamma rays, X-rays, ultraviolet rays. They all have different wavelengths, and of course, depending on the way that we generate them, they would have intensities, right? Using this electromagnetic radiation and their scattering with the atoms and molecules, people have understood how chemistry and physics can be used to generate various applications. A few I have shown here. For example, of course, without saying anything, like the LED screens that we are seeing, I'm using the computers, the chips made by the computers, and physics of phase diagrams, and the reactivity of the molecules. I just laid out a few, for example, and scattering of the atoms with the light. All that could be understood very well with the quantum theory. So the quantum theory, one could take semesters of lectures or 1 year of lectures. I'm just briefly summarizing here in the slide, has been translated into mechanics. There are varieties of mechanics under the branch of quantum theory, but one popular one is a mechanics that is driven by the wave equation. That's called Schrodinger wave equation. So the Schrodinger wave equation has been shown here on this slide, which is simply, I just spend a little time, H psi is equal to E psi, where H is the Hamiltonian operator, psi is the wave function, and E is the energy which we would like to observe either in calculations, of course we calculate it, but in experiments we would like to observe, right? So all the operators are the observable quantities. What it dictates or what it says is that if you solve this equation, we get the expression for wave function and we get the expressions for energy. Of course, if you know the wave function, you would be knowing everything about the system. That's all it talks about it. So here I have shown you Hamiltonian. Hamiltonian constitutes all the interactions of the atoms in the system, like electrostatic interactions or electron-electron interactions, nucleus-nucleus interactions, and the kinetic energy of the electrons and protons. In other words, the nucleus. So you can construct the Hamiltonian and put in the Schrodinger equation and you can solve it. But solving the Schrodinger equation is a very tedious task. It can be solved exactly for few model systems or a few realistic systems that are having just one electron. Okay, but you know, the matter around us is not just one electron and is not just one atom. It's more of molecules like benzene molecules, methane molecules, ethylene, or some drug molecules, etc. Right? So these molecules, if you want to solve, they would be having a lot of electrons, and these electrons would create a lot of trouble because these electrons are very interactive in nature. They would be interacting, and there would be sort of correlation. This is called electron-electron correlation. Including these electron-electron correlations on solving the Schrodinger equation is extremely a difficult task. And people have introduced some models. These are called quantum mechanical models, with which actually you can solve a lot of chemical and physical problems. So one that I have shown here is a very routine process. For example, Professor Desigan and group would be showing you in another few days how to solve using the Schrodinger equation using a self-consistent field model. Self-consistent field model would actually give us an approximate, a qualitatively an approximate or a quite well-converged wave function. Like I told you in the beginning, if you solve the Schrodinger equation, you get the wave function, an approximate good wave function, quote-unquote good wave function. If you know that, if you would be knowing everything about the system, right? So we can fix the wave function. These models will be explained to you by Professor Desigan down the line with some sort of particles. So you can see that. So this is a very tedious task. There are lots of programs available. One program probably you would be seeing is the Gaussian program, where you can solve the Schrodinger equation for various models, for various molecules. So you need to approximate them. So you solve that. One of the simplest molecules that you can solve maybe in a couple of seconds with as accurate as experiments. Perhaps I can even tell you, you can do using the Gaussian program or Gaussian-like software programs much better than experiments. What I mean by that, if you have two atoms like two hydrogens, you can bring them close to each other, and that forms a bond, right? The formation of the bond in the program that you calculate, we can actually see it the way I have shown you on the slide. When you bring the atoms, how do you say when you're bringing the atoms? For example, if you look at the x-axis, I have shown you the distance between the two atoms. You can play with this program, bringing these two atoms close together, and you can see the energy when the two atoms are very far from each other, and when you bring them close, the energy would come down and forms the lowest energy state for the molecule, which I have shown you here with an arrow mark indicating when the two atoms come close of that order, that is something like 0.74 angstroms, it forms the most stable configuration. So it forms the molecule. So formation of the molecule for the first time in the history of science has been shown by two popular quantum chemists, Heitler and London. As you could see on the slide, Heitler and London, using quantum mechanics, they have shown, solving the Schrodinger equation, two atoms can bind together, which means the very important keyword in chemistry is the bond. So you can see the formation of the bond between two atoms in forming a molecule. All that you could understand in solving the Schrodinger equation. You could try this out in the program that you would do in the practicals, right? So due to lack of time, I'm showing you a few details here. We can talk once I'm finishing the lecture. Okay, not just the hydrogen atom, the other important molecule is ammonia. Probably this also you could solve during your practicals. As you could see here, the ammonia molecule at room temperature would go through a barrier like the one which I have shown. Are you all able to see my mouse point here? So that is the lowest energy state. At a given temperature, it would have a barrier to go through a given transition state, which is planar in nature, and then can come down and form another energetically equivalent molecule. This is popularly called in textbook an umbrella inversion. But this won't cross the barrier. This would go through a process called tunneling without crossing the barrier. So this molecule would not cross this barrier, but penetrate through the wall of the potential well to form two equally energy state molecules, the one which I have shown on the left and right? This process only can be explained by quantum theory or quantum mechanics. We can also study a lot of more complex chemical reactions, something like I have shown an aldehyde here. You can shine a light. That's what I mean by photon, interacting with atoms and molecules. They would change their conformer for one cis to the Gauss conformer. So depending on the cis and Gauss conformer, the reactivity of the molecule would be changing. And these are certain important molecules. They would contribute to the crop generation. For example, ammonia, which I will talk to you in a minute. It's a very complex process. If you can efficiently fix the ammonia, you can have fertilizers that we all use in building the crops very productively. And the one which I have shown here would contribute to the global warming. If you can understand the chemical processes, reactivity and mechanism, by studying their conformational changes, also helps us to understand the effect of their influence in the atmosphere. For example, not just atoms, molecules, you could also study materials using a lot of spectroscopic details, instrumentation, and microscopic instrumentation, because lots of chemical reactions would take place on the surfaces. Chemical reactions would take place in the gas, chemical reactions would take place in the liquids, chemical reactions would take place on the solid surfaces and as well as in the solids, right? So all these chemical processes can be studied using quantum mechanics, either experimentally or simulations. However, doing them experimentally is extremely a challenging task, both economically and time-wise. This can be simulated using heavy high-throughput computations or high-performance computational modeling in silico. Okay, so one that I will show you as an example, you could synthesize ammonia on an iron catalyst. This is very well known, but the synthesis of ammonia on iron catalyst is very economically not very productive process. So people are now designing models, both in silico and in experiments, to understand efficiently and productively to synthesize ammonia. So what I'm showing here is a gigantic ammonia plant here, where people synthesize by following the Haber route to synthesis of the ammonia. It's not very economically productive. Okay, so I talked about atoms and molecules. What I'm showing here, the ammonia molecules, when they're condensed together, which I will be using in other part of my lecture in another couple of minutes. The one that I have shown you on the right-hand side is a very large molecule in terms of the number of atoms. It's a biological molecule, not shown in the ball and stick model. If you start showing that in the ball and stick model, you would not understand the atomic structure or the molecular structure of the molecule. So there's a form where people show in the subject field with a ball and stick, not with ball and stick, but with a ribbon and coiling models. Like I told you, solving the Schrodinger equation is extremely a challenging task, depending on the size of the system and depending on the complexity of the systems in terms of how electrons are correlated. So a number of models have been in place where you can approximately solve the Schrodinger equation. Some of these, perhaps many of you are aware of, at least in knowing the names of these models. One of the models that's becoming popular to study the molecular reactions and mechanism is a density functional theory. And otherwise, more accurate models, other than the Hattie-Fock, MP2, Moylan Plessé, and CI, in the sense configuration interaction. In other words, a couple cluster methods. As I have shown you on the slide, or others also have shown on the slides, the accuracy of the model would increase, but the computational cost would go by the increase of the number of atoms. So you have to be compromising in choosing the model that is suitable to you in understanding the chemistry and physics of these molecules. Okay, so for all these models and observations and developing theories, a lot of Nobel Prizes were given. One I would like to show you here, Kenichi Fuki, who understand not really emphasizing the accuracy of the numbers that one would get in computing. Likewise, I mean, popularly known Woodward-Hoffman rules and Hoffman way of looking at, Roald Hoffman way of looking at chemistry and physics of these molecules and materials, without really looking at high performance simulations, but looking at in a qualitative models, one could get meaningful chemical and physical solutions. For all of their contributions, a Nobel Committee has recognized and awarded them a Nobel Prize at the qualitative level of understanding chemistry and physics. Likewise, a semi-quantitative way, or quote unquote putting them in a quantitative way, looking at these energetics and wave functions, John Popel and Walter Kahn have developed wave function and electron density based models. Although for both of these methods, a Nobel Prize was also awarded in 1998. Like I showed you, it's extremely difficult to solve these models using these models biological systems. A slightly different models have been in place. They use more like force fields. And development of these force fields are in combination of force fields and quantum mechanics. Very recently in 2013, also recognized a Nobel Prize was given to these three people. Martin Karplus, Erik Warshel, Malcolm Levitt, all were given the Nobel Prize. So as you could see here, the complexity of the chemical system has largely been seen by the number of atoms and the accuracy in which you would like to obtain the information. So one has to carefully assess what one would like to have in understanding chemistry and physics, and likely choose these models based on qualitative approaches, which you would be seeing in this workshop down the line in another 3 days. Something like Huckel and extended Huckel models. You could actually solve them on any small piece of laptops or even good phones these days. You can also solve Hattie-Fock based models or density functional based models on a simple basic, even rudimentary laptops. But if you want to have those calculations carried out for large biological systems based on quantum mechanics, it's extremely difficult. Extremely difficult, even having a huge computation facility. So one needs to deviate from those models to force field based models or force field and semi-quantum mechanical based models to solve those Schrodinger equations or Newtonian mechanics based equations. Okay, so one needs to compromise. I'm just jumping from models to model to give you almost everything in one picture. Okay, I come back to the synthesis of ammonia, where we have contributed some extent recently. Not to the synthesis of ammonia, we found the leads to develop. One could productively synthesize the ammonia in silico. So as you could see here, what I have shown you, an electronic energy spectra of an ammonia, and these electronic energy levels would interact with the iron. The iron has been shown here in terms of density of states, electron density of states. They couple and would activate the N2 bond. When you activate the N2 bond, the hydrogens that are available in the atmosphere would interact with the nitrogen and form ammonia. This is the whole process. So how one could activate the ammonia bond? For example, you have to trigger some of these electrons to the unoccupied electronic energy levels, which most likely would be anti-bonding in nature, or some of them would be bonding in nature. But essentially, you have to excite some of these electrons. One of the electrons that you can excite is the highest occupied electronic energy level. Popularly, we all would call them HOMO. You can simplify that in saying it. These electrons can be excited to LUMO. When you excite it to LUMO, if it is an anti-bonding, the bond would get elongated. When the bond gets weakening, we call them bond get activated. When it's get activated, it might react to, right? So who would excite these electrons? So far in the Haber process, these electrons being excited when the nitrogen is binding to the iron 111 surface. So that's a very tedious process to excite, to activate that bond. For example, if you have a system, something like we call these electrolytes, and use these electrolytes, not the iron, and bring the N2 molecules and allow them to interact with these electrolyte supported surfaces, these electrolytes would have a freely moving electrons. These freely moving electrons can actually pumped in to some of these LUMO states, and therefore this bond can be easily activated. And suddenly these hydrogen can come down. I'm using the colloquial sentences. These hydrogens can pick up by N2, and N2 can form NH and then NH2, and finally it can form ammonia molecule. I'm simplifying to put it all that in 30 to 40 minutes. You can ask me a question if you have a query in between. So we have developed a model where we have in silico obtained a structure in where these electrons are confined in solid matrix, but they are loosely bound. And these electrons can be used in the synthesis of ammonia, for example. Followed by this work, it has been also showed in other paper very recently, talking about quantum mechanical mechanism-based hierarchical high throughput in silico screening to make the catalysis in the synthesis of ammonia. It's been in the process to verify in the labs. I'm not showing and talk about that work, but people have been working on to make catalysis in the synthesis of ammonia. Okay, so that we have done in part using in silico techniques. Okay, not just that one. One could use these quantum mechanical models to make a better catalyst than the existing ones, for example, if not better than nature. But one can also make alloys that can be robustly used in making planes. I'm serious. One can use these quantum mechanics to make alloys that are more sustainable, more profitable. I'm giving some examples. One can also make a better electrical conductors to reduce the thermal dissipation that's now we have in some sort of electric conductivity carried by the copper cables. One can ideally make superconductors, but one can make materials these days that can carry very low resistant electrical conductivity. Of course, one can also use these models to study to make better photovoltaics. Like perovskites, for example, some of you may be working on, but one can use these in silico techniques to make these materials as well. So those are few examples with that little theoretical background in rushing. We study a lot of these models using the idea of theory relatedness of data using quantum mechanics. We have been working on with that philosophy in the last 15 to 20 years, and we have contributed in making something that can be made in experiments. For example, I will show you here, we have modeled a nitrogen-rich compounds which were not made in experiments, but in silico. And then later on, very recently in 2021 and 2022, these were made in experimental labs. I just talked about lithium nitrogen compounds. These have been attempted to make a different compounds of electrolytes, and which have been used in the synthesis of ammonia very productively. Two examples I just want to talk about in the interest of time. Okay, so it's not that one would really do these things in experiments these days. We have been rightly in place with the advancements of high performance, like the one I have shown you here on the slide. You need to have really a very good computational facility to solve some of these realistic problems. But even you can solve some of the problems of molecular in nature, one need not really have very high performance computations, the one which I have shown you on the slide, but you can always use computers that are available, for example, in Vignan, to solve some of these reactions. I will show you one example. I have some backup slides. Really, you can use your laptops and PCs to solve some problems. Need not necessarily use these high performance computations, but you really need these to solve the needs of energy. For example, if you want to know to building more effective photovoltaics, you really need a high performance computing facility, probably that Vignan can think of. Okay, so those are some of the applications one could do using quantum mechanical based methods. But one should be very careful in solving these equations because these equations are very error prone. So there would be trouble in assessing the careful energetics. I would just pass on this work here, the conundrum for density functional theory, where some of the charge densities were wrongly estimated. When you are calculating in the practical sessions, be careful in picking up the right choices and the right electronic grids to calculate the accurate energetics and reaction dynamics. Okay, so I will show you one simple example here. Caution and for reading, that's what I want to highlight here. If you pick up some of the methods, we all know benzene is a hexagonal ring, but if you are not careful in picking up the right choices for right reasons, popular theoretical methods, for example, benzene, if you want to compute the geometries of the benzene, the energetics of the benzene, the reaction dynamics of the benzene, MP2, and the basis set, which would be explained to you during the practicals, you would get a wrong result. So you have to be very careful in choosing the right methods and always compare with experimental values if they are available. I mean, similarly, these days, it's frequently happening in terms of the molecular dynamic simulations. As you would see here, the title also indicates promoting transparency and reproducibility in enhanced molecular simulations. So most of these are these days due to rush and due to lack of computer time, probably most of these simulations are not reproducible. And even if they are reproducible, people who are writing these papers are not supplying all the data in a way the simulations are reproducible. And this can be done by the other well-wishers or who want to reproduce and extend the work. So one has to be really thorough in understanding these models, not using the black box models in studying the structures and reactivity. Another model that I just want to pass by in saying, so one has to also learn uncertainty quantification, even in classical molecular dynamic simulations. As has been said here in this slide, if one is not thorough and careful, the calculations are never reproducible. So one has to be patient enough to run these simulations long enough that the observations are reproducible. So I stop at this stage. With that, I think I have taken enough time to cover a bit of fundamental quantum mechanics or quantum theory to some of its applications through In-Silico. Here in IIT Kanpur, we work on various molecules and materials, which I have summarized on this slide. If any one of you are interested, please let me know. I can talk to you depending on the availability of the time. With this, I thank you all. I hope without the interruption due to the internet, I could able to communicate in the last 30 to 40 minutes. Thank you.
Can you hear me? Prasad, hello.
Yeah, hello. Yeah.
Can you hear me, Prasad? This is Prabhakar Rao.
Yeah, I could hear you. Yes.
Okay, thank you very much. And we are not sure whether, I think you might be in a meeting. We are not sure. We messaged you. And finally you made up, and thank you very much for enlightening us with your wonderful talk. And if any questions from the audience, I'll give 1 or 2 questions. So maybe I think lunchtime, I know it, but please bear with us. Any questions or interactions with him?
No problem.
Any questions?
Yeah, I would be happy to take questions. I mean, I just quickly summarized it. I know it's very loaded content, but I thought of putting it that way in the context of the talk. If you have any questions, please let me know.
Please raise your hand if you're having questions.
We can give you mic so that you can hear you.
Hello. Thank you, sir. Thank you for a wonderful
Yeah,
talk.
hello.
Hi, I'm Dr. Anandaru Goswami from Vignan. I just have a quick questions on the ammonia synthesis part. So the thing is, the calculations that you started off with, it was on iron surface, but the example that you showed, that was on ruthenium, I guess, if I remember right. So what are the changes that need to be done? Thank you.
Yeah. So the iron example shown based on the Haber process, which is very energy demanding. So now people are working on to make a better catalyst. Some of them are based on ruthenium, but what I have shown, not ruthenium, it is based on a compound that's called electride, which means the single electrons are localized in the interstitial spaces of the solid matrix or solid crystals or solid matrix. And these electrons would have very low ionization potential with which you can, pick very easily and pump into the nitrogen unoccupied orbitals, and therefore N2 bond would be activated very potentially and productively. Okay, so these substances, systems are called electrolytes, not metal-based.
Hello. Thank you, sir. So does it
Yeah,
done
no problem.
electrocatalytically then, if I remember, like for that extra electron to be pumped in towards-
No, it's not electrocatically. Electrocatically, yeah.
Hello.
I would like to take the question first. Yeah, please.
Okay. No, that's my question. I got a little bit confused on that one. Thank you.
Can you repeat the question?
My question was actually, so that means that extra electron that are already in the interstitial space, once it goes to the nitrogen, then that means it becomes electron deficient. So how we are going to replenish that remaining electron? Is it already on the electrode surface that you keep on?
That's a nice thing. Okay. The very interesting thing about these electrolytes are they're not electron deficient even after leaving the electron. These are actually electron excess. These excess electrons, in a way, quote unquote, excess electrons residing in the cavities of the solid matrix. And once these electrons are taken away by some of the reactants, the leftover material is never an electron deficient.
Oh, okay.
Okay. Yeah.
Okay. Thank you.
Any other questions?
I mean, I would actually recommend to take. Yeah, what I'm saying is, I actually suggest to take one of the N2 molecule, which would be a very good exercise if people are attempting to do that. Put that in the Gaussian and look for the electronic energy levels. You would really see an energy level that is fully occupied, which you call HOMO, and then there is an empty one. Okay, and then put an electron in N2, then make N2 as N2 minus, and then see variation in the bond length. You would be amazed that N2, which is one of the very strong bond, would be activated by elongating its distance. And this process should be done by a catalyst very efficiently. So as of now, what we have is not economically very good. So people are working on to make a better catalyst in activating this N2 molecule by keeping an electron into its one of an unoccupied energy level, which is very important in the entire synthesis of the ammonia molecule.
Thank you, sir. If any other questions are there, please ask. Because we'll be going for lunch after that. Anyone?
Okay, if there are no questions, please all of give me a big applause to Professor DLVK Prasad for his wonderful talk. Dr. Prasad, thank you very much.
Okay,
and,
thank you all.
Yeah.
Please.
I hope that you want to see personally, but we could not able to make it. Sure, next time when visiting to Wangol, please put a message so that we can invite to our university.
Sure.
So thank you very much. Nice to see you after a long time.
Thank you.
Yeah.
Yeah. See you all, and nice to see you all. Yeah.
Yeah, thank you, sir.
May I leave the Zoom?
Yeah, yes.
Yeah.
Yes.
Thank you.
So your lunch is arranged at the convocation hall. All the participants, you can go by the bus. Bus is the OAT in front of A block. Okay. So some of the scholars will be guiding you. So you can take the bus and the bus will drop you at the convocation hall. Lunch will be there. Okay. So we'll be assembling after 2. Right. So that will be at the pharmacy block. So from that, actually, you can come to the straight and one more block is there. So we'll be guiding you. Some scholars will be there, will be here. Okay. So we'll be guiding you with the venue. Right. So now we can all go to the downstairs, take the bus and go for the lunch. Okay.
For PG students, first year and second year MSc students, you can have your lunch here. And if you're anybody interested really the theoretical aspect, you can go and join there. Otherwise, first time students, you can go ahead as for your class work. Okay. Second time students, as for your mini project work, you can carry on. Really you're interested on any simulations, you can join pharmacy block. Otherwise, not necessary. Okay. So thank you once again, all PG students.